The next aging pathway is mTOR. It sounds like science fiction. Bacteria in a vial of dirt, taken from a mysterious island, created a compound that prolongs life. Researchers called it rapamycin, named after the bacteria's home, the mystical Easter Island, known locally as Rapa Nui, and famed for its rock-carved figures. Rapamycin inhibits an enzyme that came to be known as mTOR, or mechanistic target of rapamycin. mTOR has since been characterized as a master determinant of lifespan and aging. Over the hill and picking up speed. What does the enzyme actually do? mTOR is the major regulator of growth in animals, and its activation drives increases in both cell size and cell number. When we're young, mTOR is a life preserver, buoying our development, but when we're older, it can act like a block of cement chained to our ankles, pulling us under. The action of mTOR has been described as the engine of a speeding car without brakes. In this analogy, aging is a hurtling car that enters the low-speed zone of adulthood and wreaks havoc because it does not and cannot slow down. Living organisms don't have brakes because they've never needed them. In the wild, animals don't often live long enough to experience aging. Most die even before reaching adulthood, and the same used to be true for humans. Most Londoners, for example, apparently didn't even survive to age 16 during the 17th century. In the face of early-age mortality, living beings need to grow as fast as possible to be able to reproduce before dying from external causes. The best evolutionary strategy may be to run at full speed. However, once we pass the finish line, once we win the race to pass on our genes, we're still careening forward at an unsustainable pace thanks in part to this enzyme. In our childhood, mTOR is an engine of growth, but in adulthood it can be thought of as an engine of aging. Nature simply selects for the brightest flame, which in turn casts the darkest shadow. This is the so-called trade-off theory of aging, a concept technically known as antagonistic pleiotropy, in which a gene can have a positive effect when we're young and a negative one when we're old. That explains how genes with deleterious effects late in life can persist in a population. For example, the pro-inflammatory Alzheimer's gene appears to protect us against some childhood infections, major killers throughout most of human existence. Unconstrained, mTOR plows full steam ahead, revving up construction pathways to churn out cellular building blocks for new growth and canceling any plans for renovation or demolition. To preserve growth at all costs, mTOR actively suppresses autophagy, countermanding cellular cleaning and rejuvenation. In the autophagy chapter, I explained how this can lead to accelerated aging. Conversely, putting the brakes on mTOR and slowing things down appears to decelerate the aging process, extending life and health. Inhibiting mTOR is considered to be the best validated aging regulator. The soil bacteria collected from Easter Island weren't making rapamycin to slow down aging, but rather to slow down the growth of their natural enemy, soil fungi, just like fungi make penicillin to wipe out competing bacteria. Fungi, from yeast on up, have mTOR-equivalent genes, as do all plants and animals. mTOR is the universal growth regulator of advanced life forms. So, while rapamycin originally drew attention as an antifungal drug, we soon learned it had many other effects. Universal anti-aging drug. Dozens of published studies have demonstrated that by slowing down mTOR, rapamycin extends both the average and maximum lifespans of laboratory mice. What if you aren't a rodent? Rapamycin appears to be a universal anti-aging drug that extends lifespan in all animals and other organisms tested to date, the only known drug to do so. It can even work when started in midlife. The original experiment, conducted by the National Institutes of Aging Interventions Testing Program and published in 2009, was delayed because the researchers were having difficulty keeping rapamycin stable in food pellets for mice. It can't just be dissolved in their drinking water because it's fat-soluble. By the time the experiment was up and running, the mice were 600 days old, which is equivalent to like 60 human years. Even though the mice started the drug so late in life, their lifespan was extended by about 12%, which could equate to more than 7 additional years of human life. Initially, it was debated whether rapamycin was a true anti-aging intervention or merely a potent anti-cancer agent, lengthening lifespans simply by preventing cancer formation. mTOR signaling is hyperactive in up to 80% of human cancers, where it plays a pivotal role in sustaining tumor growth. When rapamycin was used clinically to prevent the rejection of organ transplants by suppressing the proliferation of immune cells that attack the new organ, a peculiar side effect was found. It made cancer disappear. In a set of 15 patients who had biopsy-proven Kaposi sarcoma, a cancer that often affects the skin, all cutaneous sarcoma lesions disappeared in all subjects within 3 months after starting rapamycin therapy. As mTOR is the master regulator of cellular growth, the reduction in cancer incidence is not surprising, but subsequent studies have shown that rapamycin can do so much more. In animal models, it extends health span too. Rapamycin has been shown to ameliorate age-related declines in cognitive and physical function, regenerate the periodontal bone that holds teeth in place, and prevent hearing loss, artery dysfunction, and tendon stiffening. It can even rejuvenate the hearts of aged mice. Remarkably, health and longevity benefits could be achieved with intermittent or transient dosing, such as receiving 1 dose every 5 days or just for a few months during middle age. As a dog dad, I was excited to read about the Dog Aging Project, where parents brought their middle-aged canine companions to be randomized to low-dose rapamycin, high rapamycin, or placebo group for 10 weeks. As in the mouse studies, rapamycin appeared to at least partially reverse some age-related heart dysfunction in the dogs without any untoward side effects. Anecdotally, most of the owners of the dogs who covertly got the rapamycin reported their pets displayed increased activity and energy compared to only a minority of those whose pooches got slipped the placebos. It was time to try rapamycin in humans. I'll cover all the rapamycin trials to date in c.nf/rapamycin. Bottom line, it's not ready for prime time as an anti-aging drug. Is there any way to suppress mTOR without taking meds? Calorie restriction. For an organism to reach reproductive age as soon as possible, it certainly makes sense to plow full steam ahead, but there are times one has to slow down out of necessity. When we were evolving, we didn't have the luxury of Uber Eats and Instacart. Periodic famine was the norm. Those who didn't slow their roll in terms of cellular growth during times of scarcity might not live long enough to pass along their genes. That's why we evolved a braking mechanism triggered by caloric restriction. Remember AMPK, our fuel gauge enzyme? When our tank is drained, AMPK switches us to energy conservation mode, in part by shutting down mTOR via 2 separate mechanisms to ensure we don't continue spending wildly while we have pennies in the bank. AMPK and mTOR can be thought of as the yin and yang of nutrient sensing and growth control. One goes up as the other goes down based on nutrient availability. Suppression of mTOR may be a central mediator of the lifespan-extending effects of dietary restriction. mTOR may also explain why women hospitalized for anorexia were found to have half the risk of breast cancer. The severe caloric restriction caused by their disorder may have tamped down the very mTOR expression that has been noted in breast cancer tumors and associated with more aggressive disease progression as well as lower survival rate among breast cancer patients. Of course, as one of the deadliest psychiatric disorders, anorexia nervosa also carries tremendous risk, but serious long-term caloric restriction is no cakewalk either. Caloric restriction has been heralded by some as a fountain of youth, but negative side effects may include dangerously low blood pressure, infertility, slower healing of wounds, menstrual irregularities, sensitivity to cold, and loss of strength, bone, and libido, as well as psychological conditions such as depression, emotional deadening, and irritability. You're also walking around starving all the time. In the infamous Minnesota starvation study that used conscientious objectors as guinea pigs during World War II, many of the volunteers suffered a preoccupation with food, constant hunger, binge eating, and many emotional and psychological issues. Even researchers who study caloric restriction rarely practice it themselves. There's got to be a better way to suppress mTOR. Protein restriction. The breakthrough came when scientists discovered that the benefits of eating less may not be coming from restricting calories, but rather from restricting protein. A comprehensive comparative meta-analysis of dietary restriction in animal models found that the proportion of protein intake was more important for life extension than the degree of caloric restriction. In fact, just reducing protein intake without any changes in calorie intake has sometimes been shown to have effects similar to restricting calories. Rats fed a diet of about 8% protein live almost 40% longer than rats fed a diet that's around 20% protein. It makes sense that protein intake can drive mTOR activation. It's not enough to have energy, calories. Construction crews need building materials. Yes, insufficient calories can shut down mTOR by cranking up AMPK, but calories aren't the primary inducer of mTOR activity. Amino acids are the building blocks of proteins. That's good news. Protein restriction is much easier and safer to maintain than dietary restriction, and it may even be more powerful because it suppresses mTOR and IGF-1, the two pathways thought responsible for the longevity and health benefits of caloric restriction. A small handful of amino acids are particularly important: methionine and the three branched-chain amino acids, or BCAA, isoleucine, leucine, and valine, so named because they happen to have fatty side chains branching off from their central structure. Restriction of these specific amino acids recapitulates many of the beneficial effects of protein restriction, which itself is the fulcrum of caloric restriction, and restricting only methionine is sufficient to extend life in a lab. So restricting all calories to boost lifespan via mTOR suppression is like fasting to manage a peanut allergy. It works, but it's unnecessary overkill. Where are these mTOR-accelerating amino acids concentrated? In animal proteins. There's more mTOR-stimulating leucine in whey protein than in comparable amounts of wheat protein. Those eating strictly plant-based diets still tend to exceed overall protein requirements, but end up taking in about 30% fewer branched-chain amino acids, including leucine, and 47% less methionine than omnivores. This translates into significantly lower levels in their blood, perhaps helping to explain the longer lives and lower cancer rates among those eating more plant-based. Tryptophan is the only other amino acid for which restriction alone can promote longevity, delay tumor onset, and increase average and maximum lifespans in rats. It's also found in lower levels in the diets and bloodstreams of those eating plant-based diets. This may also help explain the longevity of long-living populations like that of Okinawa, Japan, who had about half the mortality rate of Americans from major age-related diseases. The traditional Okinawan diet is heavily plant-centric. Only about 10% is protein, and less than 1% is made up of animal products, the equivalent of one serving of meat a month and one egg every 2 months. Their longevity is surpassed only by those regularly eating no meat at all, the vegetarian Adventists in California, who have perhaps the longest life expectancy of any formally described population in history. Individuals eating plant-based have the additional advantage of more easily avoiding palmitic acid, the saturated fat found mainly in meat and dairy that has also been shown to activate mTOR. A note of caution: those following a plant-based diet who do not ensure a regular, reliable source of vitamin B12, either through supplements or B12-fortified foods, may have elevated levels of a methionine breakdown product called homocysteine. Homocysteine is also an mTOR activator, but it can be detoxified with adequate B vitamin intake. Leucine restriction. To combat the diet-induced mTOR boost, some researchers have suggested that drugs could be developed to block some of the intestinal absorption of the offending amino acids. It makes more sense to me to just eat less of them in the first place. Leucine may be the most effective mTOR activator and is concentrated where it makes the most sense for growth promotion, in milk. Whey proteins contain the highest amount of leucine, 75% more than beef. A whey protein beverage can significantly boost mTOR activation within an hour of ingestion. Bovine milk has more than 3 times the leucine of human milk, which is reasonable because calves grow about 40 times faster than human babies. Baby rats double their weight in 5 days, so it's understandable that rat milk is more than 10 times the leucine compared to ours. Different animals have different amounts of leucine in their milk, appropriate for the growth and development needs of their offspring. No animal, except humans, drinks milk after weaning. Milk is not a simple beverage. It has a highly sophisticated hormone signaling system designed to activate mTOR. When we drink milk of a faster-growing species, especially later in life, there's a concern we may overstimulate mTOR signaling. One early visible manifestation of excessive mTOR stimulation may be acne. Acne is considered a disease of Western civilization, as it is rare or even non-existent in places like Okinawa. The acne-aggravating effects of milk drinking were first noted more than a century ago. Those who consume the most dairy have more than double the odds of developing acne as those who consume the least. 75 to 90% of commercial dairy products in the marketplace come from pregnant cows, so this may relate to the hormone content in the milk, but mTOR alone appears to increase risk, in part by promoting the production of sebum, the oily sebaceous gland secretion. Acne is considered the prototypical mTOR-driven skin disease. The fact that up to 85% of teens in Western countries exhibit acne implies overactivated mTOR signaling, and offers an explanation why a history of acne has been associated with both breast and prostate cancer risk. mTOR is upregulated in nearly 100% of advanced human prostate cancers, which may help explain why milk consumption has been found to be a major dietary risk factor for both the development and spread of prostate cancer. Milk drinkers also appear to live shorter lives, unless they drink fermented or soured milk. In the fermentation process, the lactic acid bacteria break down some of the galactose, branched-chain amino acids, and bovine microRNAs, which I'll talk about later, which may explain why yogurt intake doesn't carry the same risk. A cup of tea and broccoli. Is there anything we can eat to dampen mTOR activity? Tomato powder decreases mTOR activation in aging rats, and a tomato extract slowed mTOR in human breast cancer cells in a petri dish, but they have yet to be clinically evaluated. Broccoli compounds, however, have been put to the test. There's a compound called DIM, which is formed when the cruciferous vegetable compound indole-3-carbinol hits our stomach acid, and has been shown to suppress mTOR activation. Sulforaphane, another product of consuming vegetables in the broccoli family, also cools down mTOR, which may help explain why those who eat their greens live, on average, longer, more healthful lives. Given that hyperactive mTOR signaling may play a role in autism, researchers from Johns Hopkins and Harvard conducted a double-blind, randomized, placebo-controlled trial with an amount of sulforaphane equivalent to a few cups of broccoli a day in young men with autism, and showed benefits no drug has ever matched. Details in c.nf/autism. Is there anything we can drink to dampen mTOR activity? Exposing yeast cells to the level of caffeine that would be found in your bloodstream after a cup of coffee led to an inhibition of TOR activity sufficient to extend life. In mice, both caffeinated and decaffeinated coffee consumption was able to down-regulate mTOR to a similar extent, suggesting there's something other than caffeine in coffee that may be helping. Similarly, green tea contains the flavonoid EGCG that itself suppresses mTOR activity at physiologically relevant concentrations. This could help explain why a topical 2% green tea lotion can cut the number of pimples in half, and why green tea consumption is associated with living a longer life. What about muscle maintenance? If dietary changes are so good at suppressing mTOR, might we be concerned about rapamycin-style side effects? The enzyme is part of 2 different protein complexes, mTOR complex 1 and mTOR complex 2. Complex 1 is the aging accelerator, whereas complex 2 actually appears to be protective. Unfortunately, rapamycin inhibits both, and with complex 2 disruption come many of the adverse side effects. Protein restriction, however, targets only complex 1, so you get the best of both worlds. Is there any downside to dietary mTOR suppression? mTOR signaling is required for the bulking of muscle mass in response to resistance exercise, raising the possibility of, as one Rehabilitation Medicine Journal editorial title put it, the mTOR conundrum, essential for muscle function but dangerous for survival? However, the suggestion that leucine restriction might accelerate the rate of muscle loss with aging does not seem to be supported. Higher mTOR activation in men may help explain why they tend to live shorter lives than women, yet men experience a higher rate of age-related muscle loss. And giving months of leucine supplements with meals to elderly men did nothing to increase muscle mass or strength. In mice, blocking mTOR with rapamycin protects aging muscle. Mice genetically engineered to overstimulate mTOR suffer a catastrophic collapse of muscle mass, which is prevented by mTOR inhibition. This suggests that, if anything, mTOR may drive detrimental muscle aging. Wrapping up this aging pathway, my food for thought. The enzyme mTOR is recognized as a major driver of aging, the grand conductor of aging, if you will. mTOR seems to bring out the punny side of study authors towards a victory over aging, or, my favorite, the magic hammer of Tor. Perhaps more so than any other single anti-aging strategy, mTOR inhibition disrupts a panoply of degenerative processes, explaining why the mTOR-blocking drug rapamycin is currently the most effective pharmacological approach ever devised for targeting aging. Non-pharmacological approaches to slow this pacemaker of aging include the restriction of certain amino acids, such as methionine and leucine, protein restriction in general, or full dietary restriction. To help slow this aging pathway on a daily basis, consider following all the steps to boost AMPK from the earlier chapter, striving to stick to the recommended daily intake of protein, 0.8 grams per healthy kilogram of body weight, or 0.36 grams per pound, which translates to about 45 grams a day for the average height woman and 55 grams a day for the average height man, and choosing plant-based protein sources whenever possible.